It's just so many things to remember. Okay, so now I've actually got this thing running. We can get rid of those. Okay, so just so you know, I didn't start recording until now. And so I missed one question we went through. We talked about a little bit about the two issues from last time that I sent you an email on. And then we did number 7 and number 41. And unfortunately, I didn't have the recording on at that point. My apologies. We can talk about that tomorrow if you'd like. All right, let's get going in lesson 4.5. Limits at infinity is the topic. So what they mean by that is if you take limits as x approaches infinity. I know we haven't done a limit in a long time, but there's some really interesting there's a really interesting short way to do these when it comes to algebraic fractions. So an example of that is this one right here. Okay. So if you take a look at this function, you'll see it's a polynomial on top and a polynomial on the bottom. And you'll notice both polynomials are what? Second degree polynomials. That is, their highest power is a 2. So just think this through in this way. All right, if we were to have x get really, really large, okay, as x gets really, really, really large, I'll be honest, the 4x and the 2x don't do much. Boy, when you have a large number and you square it, that completely overpowers the entire polynomial. By the way, also -6 and -16 on the end there, those are practically worthless. So as x gets huge, what's going to happen to this? You know, really, it comes down to looking at, can't get that thing to work. It comes down to looking at just that part of the polynomial. So you've got 2 times a huge divided by 3 times a huge. It's just going to come down to 2/3. And so thanks to some shortcuts like that, we can do our limits pretty well. So I can actually write on that problem the limit as x approaches infinity of that fraction is 2/3. And let's just take a look at that in Desmos. So I got to write this down. 2x squared plus 4x minus 6 divided by 3x squared plus 2x minus 16. Okay. So let's put this in. Three x squared plus 2x minus 16. So you can see we have a rather interesting configuration, but remember the whole idea was what's the limit of this as x approaches infinity. So as we go way out here on the right on this graph, where are we height-wise? And you'll notice, well, I'm not all the way out. I'm at 48, and we're at what? Well, 2/3 would be 0.666, and you can see we're approaching that. Let's go out further. Let's try out at 170. You can see now we're 0.672. We're approaching that 0.66. We're approaching 2/3. And so this is rather interesting how, let me just come back to normal here. Bring back our, there, so we can see the roots. All right, so limits approaching infinity, we can use some rules that will greatly shorten up, and you can tell almost immediately what the limit is. So that's where we are today. All right, so let's take a couple here. So example 1, what's the limit as x approaches infinity of 5 minus 2 over x squared? So what's the limit of 5 as x approaches infinity? Well, it has nothing to do with x. So that's just 5. Okay. But that's like powerless, because what's the limit of 2 over x squared as x approaches infinity? So as x approaches infinity, that denominator is going to be huge. And what's 2 over a huge number approaching? It's approaching nothing. Okay, so let me just recap here. I wish I could get my pen to work so I can animate this a little bit. Here we go. Nope. So anyway, the point is, as x approaches infinity, that first part's just going to approach 5. And this part's going to approach nothing, right? 2 over a huge is this really, really dinky number. It's approaching 0. And what's 5 minus 0? 5. Okay, so you can see they did that down here. All right, let's do part B now. What's the limit as x approaches infinity of 3 over e to the x? Well, 3... that's not affected by x. That's just going to be 3. And what's e to the x going to be when you have infinity in for x? E to the infinity power is 2.718 to the infinity power, or close to it, is just going to be huge. And what happens when you take 3 over a huge number? It's going to approach 0. Can you see that? So yeah, let's just keep, I was going to get general rules, but let's just take another example here. Finding a limit at infinity. So here on top, we have 2x minus 1. On the bottom, we have x plus 1. And we want to know what happens when x approaches infinity. So that minus 1 and plus 1 don't mean a doggone thing, because they're so tiny in comparison. 2 times this huge number, minus 1, and this huge number, plus 1. I mean, in effect, it's just going to come down to what happens right there. Okay? And 2x over x, the x, I mean, it's just going to approach 2. So, I mean, they finally come to that down here, but here, let me just show you again. Let's do that on Desmos. 2x minus 1, x plus 1. Two x minus 1.
I have a quick question.
Yeah, go ahead.
So essentially, like, it's just like a fraction of the constants out in front of the x, or the x squared, right?
When you're doing a ratio, yes.
Okay.
So here's the graph. 2x minus 1 over x plus 1. All right, well, we want to know what happens as x approaches infinity. We use this line, this horizontal line right here is 2. And you can see, sure enough, look at, as we go out there, that thing is approaching that, isn't it? I mean, it's still like 1.9 something, but do you see the further out we go, it's approaching 2. Okay, so yeah, you're starting to see, I think that was Michaela, we're starting to see the general rule develop, and I'm glad you're doing that. And basically, here we go. Guidelines for finding limits at plus or minus infinity if you're doing fractions, you know, rational algebraic fractions. Okay, here we go. Number one, if the degree of the numerator is less than the degree of the denominator, then the limit of the whole thing is going to be 0. Because if the top has a smaller degree than the bottom, then the bottom is going to win. And you're going to wind up with something over a huge, which is going to head to 0. All right, number two, if the degree of the numerator is equal to the degree of the denominator, and here's the one you were talking about, Michaela. See, on this one, what were we doing? We were doing the degree of the top that's a first degree problem, 2x to the first, and the degree on the bottom is a first degree problem, x to the 1. So that's this rule. So if the degree of the top is equal to the degree of the bottom, then it's going to approach the ratio of the leading coefficients. That's the one you were talking about. And then rule 3, if the degree of the numerator wins, it's higher or greater than the degree of the denominator, then the limit's going to be infinity. Now, they say it doesn't exist. Because if you say, hey, the limit of that is infinity, aren't you saying there is no limit? The limit is infinity. That's saying it goes infinitely high. Oh, there's no limit. So ironically, there's two ways to say this. Okay? So let's see. Get my pen to work. We can take a quick example again. So I don't know why my pen is having problems. I got my mouse. Just be my battery. Let's take it out. Let's blow it off. See if that does any good. Yep, evidently. So like you've got 3x to the 4th over 9x to the 5th. Okay. Here, the degree of the denominator is greater than the degree of the numerator. And so when you take the limit of this as x approaches infinity, the denominator wins. That's eventually going to head to 0. When you have a tie, like 2x to the 4th plus 3x to the 3rd over 7x to the 4th minus 2x squared, you look at the leading coefficient, the one that's got the highest power on it, and you see here we have a tie. So what's the limit of that as x approaches infinity? Well, the x to the 4ths are going to be equal. It's just going to be 2/7. The limit of those leading coefficients. And then the last one, when the denominator wins, so like we have 19x cubed plus 44x squared, and the denominator has 20x to the 4th plus whatever down here. Now, the leading coefficient on the bottom is bigger than the leading coefficient on the top. So when you take the limit of that as x approaches infinity, the denominator wins and you get, I guess we did that one already, didn't we?
Are you meaning that the numerator is greater than the denominator?
Well, yeah, that's the one I should have picked. You're right. Okay, so let's just do it this way. So we plug in for here. 4, and for here, a 3. So when the numerator wins, then we move this thing over, then the limit is, you can either say it doesn't exist, and the way I like to write it is, you know, there is no limit. The limit is infinity, because you got a larger number, a much larger number on the top. Okay? So there is the summary of what turns out to be pretty simple rules for finding limits of as x approaches infinity for rational functions. Let's try another one. Limits involving trig functions. Okay, now trig is again a little different. What's the limit of the sine of x as x approaches infinity? Well, you know what the sine of x looks like in a function. It just goes up to 1, down to -1, up. It just keeps going up and down between -1 and 1. So as you go to infinity, what kind of a limit do you have? You don't, because it's forever varying. So there's one we just can't do. Okay? But we do have something kind of interesting, the squeeze theorem. So here's how the squeeze theorem works. This top graph here is 1 over x. The bottom one here is -1 over x. So that's the outside of that pink area. And when you do the sine of x over x, that's going to be stuck between those two curves. Well, we know what the limit of 1 over x is as x approaches infinity. That's 0. We know what the limit of -1 over x is as x approaches infinity, because 1 over infinity is going to be 0. So it's stuck between two other functions that have a limit of 0. So guess what? The limit of sine x over x is 0. So we have something called the squeeze theorem. So even when we can't determine a limit, if we can squeeze it between two other functions that both have the same limit, then we can use that technique. Yeah, here we go back to the more normal approach. Here we have two polynomials, one over the other. What's the limit as t approaches infinity? As t approaches infinity, take a look. You notice we got our first two. I mean, all you got to do is look at those two terms. They're tied. And what's the coefficients? 1 and 1. So the limit of this as t approaches infinity is 1. And you can see that way down here on the bottom. That's the answer they got with a lot of messing around. Okay? And here's the picture of the graph. You can see this thing is descending, then it comes back up. And what is it approaching? As you go further out here, it's approaching that line, which is 1. Okay. Take a look at another. Yeah, so let's do part A here. What's the limit of 2x squared minus 4x over x plus 1 as x approaches infinity? Look at the two leading at the high, you know, the top is a second degree polynomial. The bottom is a first degree polynomial. The top wins, right? X squared over x, the top is bigger, so that A is infinity. What's B? 2x squared minus 4x. Again, the only difference here is, you notice, very subtle. You see what this writes right here? As x approaches negative infinity, what's going to happen? Well, the top obviously wins here when you look at this. The top is a higher degree. What's the ratio? I mean, so that's going to approach infinity, but because it's x approaching negative infinity, this is approaching negative infinity. Okay. Let's take a look at these. So this one says match the function with the graphs. Okay, so all right, let's see what we got here. So the first one, what does that say? Let's see, I got to make this a little bit bigger. Yeah, well, let's just take a look at the one I circled. F of x equals x over x squared plus 2. So what's going to happen to that as x approaches infinity? Well, the top is first degree, the bottom is second degree, the denominator wins, that means it approaches 0. So which of these graphs, when you go way out, approaches 0? And the only graph you can see is, D. You see how this comes up and then it's heading down again. It's eventually heading to 0. Okay. Anyway, we'll oh yeah, this is interesting too. Let's take a look at number 2 here. Number 2, 2x over the square root of x squared plus 2. Now, I know this is grossly simplified, but what happens when you take, on the bottom, what happens when you take the square root of x squared? That's just an x, right? I know there's a plus 2, and I can't ignore that, but the 2. So the point is, you have a first-degree polynomial on the top, 2x. You have a first-degree polynomial on the bottom, x. And what's 2x over x as x approaches infinity? 2. So this one is approaching 2 when you get out to infinity. All right, well, that could be A. It could be E. I mean, there's all kinds of them approaching 2 here. It could be C. So at least we've got it narrowed down. Okay. Let's see. What else can we do? What about, what happens when x approaches negative infinity in number 2? All right, so on the top, you've got 2x. On the bottom, technically, you have x. And so let me just try to simplify this. So in effect, you've got 2x over x. What's the limit of that? We already know as x approaches infinity, that's going to approach 2. What about when x approaches negative infinity? Well, that's going to be positive 2, right? Because 2 times a negative infinity is negative 2 infinity. And the bottom, you've got negative infinity. It's going to be a positive. It's still going to approach 2. Okay, so now we can eliminate C. Because you see how that graph is approaching 2 to positive infinity. It's approaching negative. Now, that's not it. A could still work. E could still work too. Do you see how this is approaching 2 from the right and it's approaching 2 from the left? So it could be one of those. It could also be F. All right, so you see how we're narrowing it down. All right. Let's see, what else can we do? Let's take a look at what that looks like. 2x over the square root of x plus 2. 2x over square root of x plus 2. Got to come back to reality here. Okay, so you see what's happening there. This graph is approaching Boy, what did I do? Oh, that's supposed to be x squared plus 2. There we go. So now we can see what's going on. It's approaching. We should be, this one is approaching 2 to the right, and it's approaching negative 2 to the left. Why is that? Because when x approaches negative infinity, you're going to have on top a negative infinity. On the bottom, what happens when you take a negative infinity and square it? It's going to be positive, square root's positive. And then a negative divided by a positive is a negative. So when we come back here, this looks like this is our answer to number 2. So we got to keep looking for clues. Let's see. Here's some examples from the assignment. Find h of x. Find the ratio limit as x approaches infinity. So what's the limit of h of x as x approaches infinity? Okay. Now f of x, I don't know why, but they wrote it up on top here. So you've got this thing, 5x cubed minus 3x plus 10x over x squared. So you got to construct this yourself. You got that? So this problem is actually 5x cubed minus 3x squared plus 10x all over x squared. I don't know why they just didn't write it out, but that's A. What's the limit of this thing as x approaches infinity? Well, because the numerator wins, this is going to be infinity, right? Okay, what's going to happen on 14a? So you take that, it's a negative 4x squared plus 2x minus 5, and put that over x. What's the limit of that as x approaches infinity? Well, the numerator wins. And what do you have on the, but because that there's a negative there, what's negative 4 times infinity? It's going to be a negative, so that one's going to be a negative infinity. Okay. Let's see. So let's take B, 13b. So this is 5x cubed minus 3x squared plus 10x over x cubed. Now take the limit of that as x approaches infinity. Notice we have a tie in degree between the top and the bottom. So this is a Michaela problem. Because we have a tie, what's going to be the limit, Michaela?
Five.
Yep. Thank you. Sorry I put you on the spot there, but your rule works. Let's take a look at 14b. So we take this negative 4x squared plus 2x minus 5, and it's over x squared. Notice here too, we have a tie. We have a tie. Therefore, it's the limit of the coefficients. What are the coefficients? Negative 4 over 1. So that limit should be negative 4. All right. Let's go down to this next section. Limits at infinity. So what's 15a?
Do not exist.
What's that?
Undefined, like do not exist, because numerator is bigger than the denominator.
15a, the denominator is bigger than the numerator.
Oh, yeah.
So you're going to have, so in other words, you've got this number on the top over this huge number on the bottom. that's going to approach 0, okay, because the denominator wins. How about B? Here we have a tie. We have a tie, so we look to the coefficients. 1 over 1, 1. How about C? Numerator wins. Okay, let's look at 16. 3 minus 2x. Okay, so what's the degree of the top? X to the first. What's the degree on the bottom? X cubed. So the bottom wins, okay? And so that's going to go to 0. Part B. Top, we have 2x, negative 2x. On the bottom, we have 3x. As x approaches infinity, we're going to use the, what happens when you have a tie? It'll approach the coefficients. The coefficient on top is a negative, and the one on the, so you'd have to write that one as approaching negative 2/3.
Question.
Yes.
For 15a and 16a, why is not like approaching to infinity?
Why is it? Okay. When the denominator is bigger than the numerator, then you're going to wind up with this little tiny fraction. Okay, and because it's heading to infinity, it's going to get so tiny that it's heading towards 0.
Okay.
So if we looked at, take a look at a graph of 15a. X squared plus 2, let me write this down. X squared plus 2 over x cubed minus 1. X squared plus 2 divided by x cubed minus 1. So as x approaches infinity, what's going to happen? You see how it's heading to 0. So you're looking way out here to the right, and you can see it's not there yet, but it's heading, it's 0.033 here. You go out here, it's 0.025. It's heading for 0. So when the denominator wins in a limit where x is approaching infinity, you're heading for 0. Okay, where was I? Yeah, I think so. What I'm going to do here is I'm going to show you what the assignment is, but we're going to take an extra day. Okay, we ran out of time here, which is fine. So let me go down to let me show you what the assignment's going to be. It's just going to be 13 to 41 odds. Okay, but I just don't feel comfortable setting you off quite yet. We're at kind of the end of class, and we need to spend a little more time with this. But let me I'll leave you with this. These 3 guidelines really is kind of the bottom line of this whole thing is, and that is, I know you can't see all the writing, but that's fine. Anyway, when you're doing a rational function, that's a fraction, algebraic fraction. If the degree of the numerator is smaller, then, and this is the one we were just talking about, Richard, then as x approaches infinity, the thing is going to be heading to 0. Number 2, if the degree of the top is the same as the degree of the bottom, then it's going to head toward the ratio of the leading coefficients. And number 3, if the degree of the numerator is bigger than the degree of the denominator, then it's going to head for infinity, or as it says, so really we could just add to this that, can't get this thing to work again. Anyway, it's going to head for infinity. So we'll come back. We'll talk about this some more on tomorrow. Okay, well, thanks for hanging in there with me. Anybody have any questions? I'd like you to, why don't you just get started? You know what the assignment is going to be, and let's see how it goes. We can talk about it some more tomorrow and wrap it up. Well, thank you. I appreciate it. What do we have here? 4 people. 1, Richard, 2, 3 people. Thank you for being here.